Our third speaker this morning is Sir Martin Rees, who I think is one of the few physicists who rivals Freeman in his willingness to examine radical departures from conventional views of the universe. Martin is Britain's Astronomer Royal. He's the past master of Trinity College at Cambridge. He's the past president of the Royal Society of London, and for 20 years held the position of Plumian Professor at Cambridge. He's made fundamental contributions to almost every subject in extragalactic astronomy and cosmology, particularly to gamma ray bursts, black holes, galaxy formation, and a number of aspects of relativistic astrophysics. He's had a long association with the Institute, having first come here as a member in 1969. He's returned regularly since then, and we've had the benefit of his service as a trustee of the Institute for the past 15 years. Martin.
Thank you, Scott. It's a great privilege to be here today to celebrate a man to whom I owe a great deal, both intellectually and in personal kindness. Ever since I first came here as John Bacall's first postdoc just over 40 years ago. Freeman and I have one thing in common. We were both undergraduates at Trinity College. And Freeman was, of course, especially precocious and brilliant. We heard about his undergraduate maths papers yesterday. But he wasn't Trinity's best undergraduate. That was... yes. Yes. That was the great Isaac Newton. And Isaac Newton must have thought about going into space. This picture from the English version of Principia shows, in my view, still the nicest way to explain pedagogically the concept of orbital flight. And Newton calculated that the cannonball from the mountaintop would have to go at 18,000 miles an hour to go into a circular orbit. And that, of course, as we know, wasn't achieved until 1957, when the first Sputnik went up. But by that time, Freeman was again thinking far ahead, because that's when he worked on the Orion nuclear-powered rocket project, which I guess is, again, 200 years into the future. And he continues to be fascinated by interstellar travel, alien life, hyper-advanced technologies, etc. Today I'm going to focus not on those, but on another of Freeman's interests, cosmology. How complexity and variety emerges, the fabric of space-time on the largest possible scale, and the far future. But first, a few more parochial comments cosmologically on the ingredients of our cosmic habitat. We've heard this morning about the ubiquity of extrasolar planets, one of the most exciting growth points in astronomy with potential links to biology. And I think Sarah Seeger emphasized these systems display great variety, and essentially none of the details have been predicted. But the existence of planets wasn't surprising. We've in fact come to expect them as a natural consequence of star formation. That's because, according to this cartoon, stars form by contraction of a dusty cloud, contracts, conserving angular momentum, spins off a dusty disk around it. And so we're not surprised that planetary systems are ubiquitous. But let me give another flashback to Newton. He famously explained why the planets were moving in elliptical orbits, but he was puzzled as to why they were moving in the same plane and all orbiting the same way around their star. Yeah. Yes. Yes. Sorry about that. Yes. What about stars and atoms? We see stars forming in places like this, and we see stars dying. This is what the sun will look like in 6 billion years. And here's the remnants of another star. And this, as I'm sure most of you recognize, is the Crab Nebula, the relic of a star which the Chinese astronomer royal recorded in the year 1054 AD. Now, just before this supernova exploded, a slice through it would have looked like this. Onion skin structure with the hotter inner layers processed by nuclear fusion up the periodic table. And the material is then flung out into space. And it orbits into the interstellar medium. And this is important because this is relevant to the origin of the atoms which made the stars. And we now know that all the atoms that we are made of were produced in ancient supernova which exploded, their material was recycled into new stars. There's a sort of ecological flowchart, which I won't describe in detail, which is going on inside our galaxy. And in fact, the people who developed this more than 50 years ago were Margaret and Jeff Burbidge, Willie Fowler, and Fred Hoyle. And this was taken actually for Willie Fowler's 60th birthday party in Cambridge, where he was given a model train as a present, as you can see. So for 50 years, we've been able to push back the causal chain still further. We now know why the planets are in planar orbits from the disk. We now know, and have known for 50 years, thanks largely to these people, why carbon and oxygen are common, why gold and uranium are rare, and how they came to be in our solar system. But tracing the causal chain further back to understand where the original protons and neutrons came from and the first stars takes us into the extragalactic realm. Here's Andromeda, which is the nearest big galaxy to our own, spinning disk viewed obliquely, with 100 billion stars spinning around a central hub. And here's another galaxy seen face on. And we have huge samples of galaxies to study. But how much can we actually understand about galaxies? Physicists who study particles can probe them and crash them together in accelerators. Astronomers can't crash real galaxies together. And galaxies change so slowly that we see, as it were, just a snapshot of each one. But we can do experiments in a virtual universe. We can ask what would happen if two galaxies spiral together. And here is such a virtual collision, seen 10 to the 15 times faster than in real time. Everything in each galaxy exerts a gravitational pull on everything else, causing distortion, tidal plumes, and so forth. And this will happen, by the way, when Andromeda hits our galaxy in 4 billion years, so be warned. Now, we see this sort of train wreck when the galaxies merge, and when we look in the real sky, we see things like this. And having done those simulations, we can infer that if we came back in 10 to the 8th years, we would find that these two galaxies, tidally affecting each other, will have merged into a single galaxy. Now, we can do simulations like this and of galaxies, making different assumptions about the masses of stars and gas in each galaxy, and see which matches the data best. And importantly, we find by this method and others that all galaxies are held together by the gravity not just of the stars and gas we see, but of the famous dark matter. Galaxies are embedded in a swarm of invisible neutral particles, which collectively contribute about 5 times as much mass as the ordinary atoms do, the dark matter. I mentioned just 3 other lines of evidence for this. One line of evidence is that in a cluster of galaxies, if you measure the relative velocities of the galaxies, you'd find the whole cluster would fly apart unless there was more mass than you see in gas and stars. And the first person to find this was Fritz Zwicky, who I show because I know he's one of the scientists who Freeman Dyson, in my view, quite rightly admires and thinks is underappreciated. The second technique is to note that if there's gas in a cluster of galaxies, then if you can measure its temperature, then you can estimate how deep the potential well is that's holding it in. And X-ray measurements, this is a map of a nearby cluster, show very hot gas, which is being churned around by activity, but its temperature allows you to infer how deep the potential well is, and this again gives the evidence that there's about 5 times as much dark matter as what we see. And a third method, which Einstein would have liked very much, is gravitational lensing. In this picture, the bright objects on the left-hand side are galaxies in a cluster about 1 billion light years away. The fainter objects are galaxies several times further away still. And you see the distorted streaks, and that's because the cluster is acting like a poorly figured converging lens and affecting the background objects. And by doing simple optics, you can infer the mass of the cluster, and again, it's about 5 times larger than the mass of what we see. And here in round numbers is what we find. We find that if we take a fair sample of the universe, ordinary atoms, baryons, contribute about 4% of the so-called critical density. This is a density a universe would have to have if gravity and kinetic energy were in complete balance, as it were. But the dark matter is about 6 times more than that. We can test our ideas on how galaxies form by observing eras when they were younger. We can look back 1 billion, 2 billion, 3 billion, 4 billion light years and see what the universe looked like then. And this picture, this is the extreme Hubble Deep Field, which shows a tiny patch of sky, just a few 2 arc minutes across. And even in that tiny area of sky, you can see these hundreds of smudges, each a galaxy, some fully the equal of our own, looking so small and faint because many of them are 10 billion light years away and are being viewed when they've only recently formed. And this smudge here is, in fact, the most distant object of which we have a really good spectrum. This is a spectrum of that object. I showed the tracing, and the only point I want to make is that the peak on the left is Lyman alpha of hydrogen, normally in the far ultraviolet at 1216 angstroms, but shifted, stretched by a factor of 8, and now at about 1 micron in the infrared. This object, incidentally, is not a normal galaxy, it's a quasar, where the light from the stars and gas is being boosted by light energized by a central black hole. And this black hole is producing far more energy than all the stars. And, of course, we are therefore observing one of the most remarkable predictions of Einstein's theory when we look at these distant objects, but that's another story. Now for a more fundamental question. Our present complex cosmos manifests a huge range of temperatures and density, from the blazingly hot stars to the cold night sky. But the microwave background, the 3-degree Kelvin pervading all space, is an afterglow of a phase when the entire universe was amorphous, uniform, and hot. And people sometimes wonder how the intricate complexity of the present universe emerged from this amorphous fireball. It might seem to violate the second law of thermodynamics, where normally patterns decay or disperse. But the answer to this seeming paradox lies in gravity, which has odd thermodynamic properties. Gravity enhances density contrasts. Any patch of the early universe which started off slightly denser than average would lag behind more and more as the universe expanded. And it would eventually stop expanding and separate out. And this movie, where the expansion is scaled out, shows a simulation of part of a virtual universe, a domain large enough to make a lot of galaxies. You can clearly see the incipient structure unfolding and evolving as the universe expands, and the time step at the bottom is in gigayears. Here's a more detailed simulation that distinguishes the dark matter from the baryons which can radiate, dissipate, and form stars. So the blue shows a dark matter clustering to make a galaxy, and the red shows the baryons, the material made of atoms, which condenses more, dissipates, and eventually will form stars. And then the convening power of gravity, as it were, continues. And in fact, Freeman Dyson wrote a famous Scientific American article many years ago where he clearly explained how gravity always wins in the end, but there are various sort of hang-ups, nuclear energy, angular momentum, etc., which keep the universe going for a long time before gravity's final victory. Now, there's one important point about these simulations. The initial conditions fed into the computer model aren't arbitrary. They're derived from the observed fluctuations in the temperature of the microwave background, which expanded from very early eras. The microwave background's smooth except for fluctuations of about 1 part in 10 to the 5th. But computing forward, those fluctuations are amplified into the structures of the present universe. These fluctuations were first beautifully observed by WMAP, a project initiated by the late David Wilkinson here at Princeton. But the slide I show here is more recent and precise data from the European Planck spacecraft. And these fluctuations can be studied in detail. And this graph, due to Max Tegmark, illustrates the success of this theory. The solid line shows the RMS density contrast as a function of scale, which you would expect based on this theory. And the data points show what we know about the density contrasts on all scales, cluster of galaxies, and down to smaller scales. So it's a real vindication of the idea that the structures of the universe now emerge from the fluctuations which are traced in the early universe by the microwave background. Here's a time chart of cosmic evolution from the hot, dense beginning to today's complex cosmos. And we can trace back to the microwave background, last scattered at 300,000 years, right back to 1 second, when hydrogen, helium, and deuterium were produced at the temperature of an MeV, and perhaps with confidence right back to about a nanosecond, which is when the temperature was 50 GeV, about the energy that could be reached by the LHC. And at that time, incidentally, everything we can now see out to the limit of our telescopes would have been squeezed down to the size of the solar system. But if we want to ask more basic questions, where did the fluctuations come from? Why is the universe the observed mix of matter, radiation, and dark matter? Then we have to go back still further. Indeed, we have to go back, many people think, to a time when the entire observable universe was squeezed not to the size of a solar system, but to the size of a tennis ball. This was the cover of a magazine. According to a popular theory, the entire universe inflated from a region no bigger than that. I'll come back to this early universe in a minute, but now let me digress to talk about the future of the universe. A few years ago, cosmologists had a big surprise. It doesn't change anything I've said about the past of the universe, but alters our perspective on the far future. There are 3 textbook scenarios for the future of the universe, the way the scale factor changes. On the left, we have the recollapsing universe. And 40 years ago, when I first came here, John Wheeler was advocating this. The idea the universe had to be a finite closed system. That was the most popular idea. 20 years ago, most people would have bet on the middle version. The idea the universe went on expanding forever, but decelerating. But it turns out that it's the right-hand picture. The universe is now speeding up. On the cosmic scale, gravitational attraction is overwhelmed by some mysterious new force latent in empty space, which pushes clusters of galaxies away from each other. And there are two interlinked arguments that have led to this picture. The first, shown bottom right, and probably best known, is that if you do the Hubble diagram for supernovae, you find that the universe was expanding slower 5 billion years ago than it is now. It's accelerating. But there's another argument which comes from looking in detail at the microwave background fluctuations. The microwave background fluctuations have properties that can be predicted. There's a particular length scale, which is essentially the horizon scale at the last scattering surface, which is like a sort of rigid rod whose size you can predict. Now, if you know that you've got a certain size, then if you measure the angular size, then you know the geometry. You know whether it's flat, so that a triangle has 180 degrees angles, or not. And the observations show that the geometry of the universe is flat in that sense. And that therefore means that since we know that the dark matter and baryons only contribute 30% of the critical density, something else must make up the other 70%. And that something else must be uniformly spread, and moreover, it must have a negative pressure, because it wasn't important in the past. So in fact, even without the supernovae, the microwave background would have allowed us to predict the acceleration, because we'd have predicted the universe was dominated by stuff with negative pressure, and in Einstein's equations, negative pressure perversely gives you an acceleration. But this network of arguments is why we are confident that the universe is now accelerating. The nature of the dark matter may well be pinned down quite soon. We don't know what it is. We may learn from the LHC or from direct observations. But this mysterious repulsive force, the vacuum energy, I think won't be understood until the string theorists have given us some picture of the graininess of matter, the graininess of space. And the graininess of space is expected to be on a scale a trillion times smaller than an atomic nucleus, where gravity and quantum theory meet. So, although the world experts are based here, I'm not holding my breath for a theory that will do that. Now, another basic question. How much space is there altogether? How large is physical reality? Well, we can see a finite but very large volume out to the limits of our telescopes. But that's essentially because there's a horizon, a shell around us, delineating the distance light can have traveled since the Big Bang. But that shell has no more physical reality than the horizon around you if you're on a boat in the middle of the ocean. You don't think the ocean stops just beyond. There's no perceptible gradient across the part of the universe we can see. If you look as far as you can that way and that way, things don't differ by more than 1 part in 100,000. So most people would suspect that the universe goes on for probably thousands of times further than we can see. And it may go on far further, so far that all combinatorial possibilities are repeated. Far beyond the horizon, we could all have avatars. But be that as it may, even conservative astronomers are confident that the volume of space-time within range of our telescopes, what astronomers have traditionally called the observable universe, is only a tiny fraction of the aftermath of our Big Bang. We'd expect far more galaxies beyond that. Moreover, if the acceleration persists, those galaxies beyond the horizon now, rather than coming into view, will get further and further out of view. But that's not all. Plausible models for the 10 to 16 GeV physics lead some of them to so-called eternal inflation, shown in this cartoon. This is just one of many models for the ultra-early universe. They suggest that our Big Bang, shown with its horizon bottom right, could be just one island of space-time in a vast cosmic archipelago. Now, when the multiverse is mentioned, people say these domains aren't observable, so they aren't part of science. But I want to contest this by sort of aversion therapy. You know, that's when you start off with a little spider a long way away and end up with tarantulas crawling all over you. I mentioned that there were galaxies beyond our horizon. We're relaxed about that. But we realized that because they're accelerating away, they'll never, even in principle, be observable. So they're the aftermath of our Big Bang. But why is their reality status necessarily higher than that of the aftermath of other Big Bangs? But of course, we don't know yet if there are other Big Bangs. It depends on the uncertain physics. We'll only take their existence seriously if they're the predictions of a unified theory that applies to the ultra-early universe at 10 to 16 GeV and gains credibility by being battle-tested by experiments and observations in other way. We need to have many tests of a theory, but if we had many tests, then we believe even in unobservable consequences. So a challenge for 21st century physics is to decide which branch of this decision tree is correct. First, on the left, are there many Big Bangs or just one? Second, if there are many, are they all governed by the same physics or not? Do they all cool down the same way or differently? Many string theorists think the latter. They think there could be a huge number of different vacuum states, which would give rise to different microphysics. If they are right, then what we call the laws of nature, which are universal within the part of the universe we can see, would, in this grander perspective, be just local bylaws governing our cosmic patch. Many patches could be stillborn or sterile, because the laws prevailing in them might not allow any kind of complexity. We therefore wouldn't expect to find ourselves in a typical universe. Rather, we'd be in a typical member of the subset where an observer could evolve, the so-called anthropically allowed subset. And these ideas motivate us to explore what range of parameters would allow complexity to emerge. Now, I should mention that some people are allergic to anthropic arguments. It makes them foam at the mouth. But they can regard this as an exercise in counterfactual history. Just as some historians speculate about what would have happened if the Brits had fought better in 1776. And biologists speculate on what the biosphere would have done if the dinosaurs hadn't been wiped out. So, in some spirit or other, it's interesting to highlight several prerequisites for the emergence of our complex and structured cosmos. Let me give a list. The first, clearly, is gravity, which enhances density contrasts and binds structures, as I've shown. It's a very weak force. On the atomic scale, it's about 40 powers of 10 weaker than the electric force between proton and electron. And this is my favorite pedagogical diagram. It's a diagram of log mass, upwards, log radius, across. Black holes, line of slope 1 there. And note that a black hole the size of a proton has the mass of about 10 to 38 protons, manifesting the weakness of gravity. And there's a line of slope 3 for ordinary solids. Sugar lumps, asteroids, and planets. Gravity is unimportant up to asteroid-sized lumps. It makes planets round, and any object more massive than Jupiter is squeezed to make a star. And right on the left is where quantum theory and gravity meet, the Planck mass, where a black hole is no bigger than its Compton wavelength. This is familiar basic physics, but one point I want to make is that if gravity wasn't so weak, this graph would have basically the same shape, but the scale, the vertical scale, would be more compressed. There wouldn't be so many powers of 10 between the micro and cosmic scale. Less space and time for complexity to emerge. So, an interesting universe must have very weak gravity. It's sometimes said, incidentally, that gravity is fine-tuned. That's not true. If gravity was 10 times weaker, it might be even better, because then stars would be 30 times heavier, would last 10 times longer. It's important that this large number is very large, but if it was even larger, that might be even better. Now, there are other requirements. There could be no complexity if the universe stayed in thermal equilibrium, as it was for its first 500,000 years. And there must be an excess of matter over antimatter. Otherwise, as the universe cooled down, it would all annihilate, and we just have radiation now, and we wouldn't be here. Another requirement is that chemistry should be non-trivial. There must be a possible periodic table, and that requires a sort of tuning between nuclear and electromagnetic forces, because we could clearly not have complex chemistry nor nuclear fusion if we only had hydrogen. Also, there must be some stars to form, and maybe second-generation stars to have planets around them. And there must be a tuned expansion rate, so that the universe neither expands so fast that galaxies can't form nor contracts. And that's what inflation and other ideas have told us about. And there must be non-zero fluctuation in the early universe. Otherwise, there would be still now no structures and no people. So the aftermath of the Big Bang is determined by some basic numbers. And if we plot these in a multidimensional graph, there'll be one or more anthropically allowed areas within which complexity could emerge. I'd like to illustrate this by focusing on two parameters which I've already mentioned. The first is lambda, the vacuum energy. And as is well known to physicists, we know if it was bigger, if the cosmic pulse was stronger, then it would take over and overwhelm gravity before galaxies are formed. Also, it can't be too negative, otherwise it would make the universe collapse too soon. I want to mention another number, which is perhaps not so well studied, which is the fluctuation amplitude, how rough the early universe is. It's measured by a number I call Q, which is the curvature fluctuations generated in the early universe. This number Q measures the fluctuations in the microwave background. In our universe, it's about 10 to the minus 5. It also determines the binding energy of bound systems, and it determines the scale over which the universe now is lumpy by very simple factors. And our universe has Q of 10 to the minus 5. And bound systems like clusters have a binding energy 10 to the minus 5 mc squared, velocities of 1,000 kilometers per second. Now, what would the universe be like if Q was different? If the universe was very rough, more than 10 to the minus 3, then structures would start forming early on, and you get huge black holes collapsing, and you get no stars and no galaxies. So Q greater than 10 to the minus 3 isn't very good. But Q could be larger than our actual value. It could be 10 to the minus 4. This might be a rather interesting universe, because what would happen then is that structures will condense out 10 times earlier than in the movie I showed and get much bigger. So you'd have huge galaxies, huge disk galaxies, the mass of a cluster of galaxies forming at a redshift of 10, huge disk galaxies. And this might be a good universe to live in. The only downside is that the stars will be packed closer together, so it might be hard for a solar system to remain undisturbed by a passing star for long enough. On the other hand, if Q is much lower than in our universe, then we have a sort of anemic universe where the gravitational potential wells are condense out late, and have shallow potential wells. You might get a few stars, but the gas will be blown out, and if Q was too small, then we wouldn't have any structures. So Q is not fine-tuned, but must be in the range 10 to the minus 4 to 10 to the minus 6. Now, what we would like to do, perhaps, is to understand enough about these parameters to be able to plot out the area where life could exist. And Mary Olivia and I did this just for two numbers, Q and lambda. And we have the upper limit on lambda, which depends on Q. Now, what we don't know at all, apart from whether there are these multiverses, is what are the relative probability of different points in this shaded area. We know where we lie in this universe, but the question is, should we be surprised that we are not in a universe with a lambda 1,000 times higher, which would be allowed if Q was 10 times higher? So we don't know how typical our location is. And this would require not merely understanding these numbers, but having a measure on the relative probability of different parts of this parameter space. Well, these explorations are interesting for delineating the anthropically allowed range. But remember that these arguments are irrelevant if the constants are unique. But otherwise, they're the best explanations we'll ever have for the actual values of these constants. It's reminiscent, actually, of planetary science 400 years ago, even before Newton. At that time, Kepler thought that the Earth was unique and its orbit was related to other planets by beautiful mathematical ratios, the Platonic solids. We now realize, of course, that there are zillions of stars, most for planetary systems, and Earth's orbit is special, only insofar as it's in the range of radii and eccentricity is compatible with life. So maybe we're due now for an analogous conceptual shift on a far grander scale. Our Big Bang may not be unique any more than planetary systems are. Its parameters may be untidy environmental accidents, just as the details of the Earth's orbit are. The hope for neat explanations in cosmology may be as vain as Kepler's numerological quest. Well, it may disappoint some physicists if one can't determine these fundamental numbers from simple equations. But in compensation, we'd realize that space and time were richly textured, but on a scale so vast that astronomers aren't directly aware of it. Any more than a frog, whose universe was one pond, would be aware of the world's topography and biosphere. So this concept should appeal to Freeman. At a conference in Stanford a few years ago, there was a panel discussion where the panelists were asked how strongly they'd bet on the multiverse concept, which is still speculative. I said that on a scale, would you bet your goldfish, your dog, or your life, I was nearly at the dog level. Andre Linde said he was far more confident. He'd spent 25 years of his life on this inflationary universe story, so he'd bet his life on it. And then Steven Weinberg later said he'd happily bet Martin Rees' dog and Andre Linde's life. Next, a few words about the far future. Long-range forecasts are never reliable, and the biggest uncertainty about the far future is about the behavior of this energy in empty space. Is it really constant, or does it change? If this energy in empty space were to go to zero and even reverse, then we could have the big crunch, as Wheeler like 40 years ago. On the other hand, there's another even more speculative scenario called the big rip, which is that if the force in empty space gets stronger, it would start tearing apart galaxies and then stars and then us. This is another rather speculative scenario. But the best and most conservative bet is that the repulsive force is unchanging, Einstein's lambda in a modern guise. And then what will happen is that the galaxies accelerate away and disappear over an event horizon, rather like an inside-out black hole. And all that's left will be the remnants of our galaxy, Andromeda, and smaller neighbors. Protons may decay, dark matter particles annihilate, occasional flashes when black holes evaporate, and then silence. Well, that's the case if we assume that nature takes its course, as it were. But that wasn't enough for Freeman. He asked the question, what would happen if there were no technological limitations and advanced life could engineer on a cosmic scale? Indeed, he had his classic article in Reviews of Modern Physics around 1980. His aim was, I quote, to establish numerical bounds within which the universe's destiny must lie. The question was, could an unbounded amount of information be processed? Could an unbounded number of thoughts be thought if all material was optimally converted into some computer or superintelligence? Well, in fact, I'd, more than 10 years earlier, written a juvenile paper discussing a recollapsing universe. This sort of eschatology, which I envisage, is a depressing one. which our remote descendants will eventually fry as the temperature rises during the cosmic recollapse. In his paper, Freeman referred to my work, saying that this miserable end in a closed universe gave him claustrophobia. That's why he focused on the ever-expanding case. And as he said in his article, the best prospect for infinite subjective time will be an Einstein de Sitter universe which decelerated so that arbitrarily large amounts of material eventually come within the horizon. But as I've said, the cosmos we seem to be in, the aftermath of our Big Bang, is one where the amount of matter within the horizon is going down, not up. So unless our descendants engage in cosmic scale engineering to, as it were, lasso distant galaxies and bring them back before they disappear, then eventually only the remnants of our local group of galaxies will remain within the horizon. And then there's a definite upper bound to complexity and information processing. So maybe this is relevant to Freeman. Freeman doesn't really feel happy and at home in our cosmos, but perhaps it's some consolation to him that if indeed there's a multiverse, he will have avatars in cosmoses with far greater potential than our own. Well, fortunately, perhaps time won't allow me to develop these speculations further. But as this is the last talk of the morning, I'd like to end with a cosmic vignette that segues into the afternoon session and focuses back a bit more towards the here and now. We're all familiar with this iconic picture. But suppose that there were some aliens out there who'd been watching our planet for its entire history. What would they have seen? Over nearly all its life of 45 million centuries, Earth's appearance would have changed very gradually. But then changes accelerated as the Anthropocene began. And within just 1 century, they'd have seen the carbon dioxide in the atmosphere begin to rise enormously fast, the Earth becoming a radio transmitter, the integrated effect of radios and radars, and something else unprecedented happened. Objects launched from the planet's surface were projected into orbit, journeying to the moon and the planets. If they continue to keep watch, what might these aliens witness in the next century? Will this spasm of activity be followed by silence? Or will the planet's ecology stabilize? And will rockets launched from the Earth spawn new oases of life elsewhere? And, of course, there is plenty of time ahead. Post-human evolution, here on Earth and far beyond, could be far more prolonged than the Darwinian evolution has led to us. Goes on almost forever, and I like Woody Allen's quote, "Eternity is very long, especially towards the end." Moreover, future evolution not only has plenty of time, but it won't happen by Darwinian selection, as Darwin himself thought. It'll happen far faster, on a technological timescale. Human pioneers living on planets, or maybe on comets, they would surely use genetic knowledge to modify their progeny to adapt to an alien environment. New post-human species could emerge within a few centuries, far faster than natural selection. And remember, the Earth has 6 billion years ahead, so any creature witnessing the sun's demise will be as different from us as we are from a bug. Indeed, they won't be organic. And as Freeman has shown, robots may be pursuing by then cosmic engineering projects with stupendous, albeit not quite unlimited, prospects. But my final thought is this. Even in this concertinaed timeline, extending millions of centuries into the future as well as into the past, this century is special. It's the first in our planet's history where one species, namely ours, has Earth's future in its hands and could jeopardize this immense potential. So this pale blue dot in the cosmos is a special place. It may be a unique place, and we're its stewards at a especially crucial era. And that's a message for us all, whether we're astronomers or not, and we should all thank Freeman for conveying it so eloquently and inspirationally. Thank you very much.